Hi there, I'm Mr. Dewis, and we're going to be talking about electric potential. Welcome to AP Physics 1. So we are talking about electric field to start, just to kind of recap a little bit. So electric field, remember, is force per charge. And what I'm going to do is I'm going to make this statement where work is equal to force times distance. But wait, if I can then rearrange this equation up here to say that the electric field times the charge, sorry, I forgot a little hash there, is equal to the force, then I'm going to substitute that in for the force down here in my work equation. So that means that this is equal to E times Q times D. And it's usually written like this. It's usually actually written QED, and that's the way it's typically written. So there's a little bit of derivation there on work and how it relates to the electric potential of a system. Alright, so let's look at a basic setup where we have two plates here. One on the left we have a positively charged plate, and on the right we have a negatively charged plate. And between these two plates we would have an electric field that extends from the left plate to the right plate. So it would look something like this. I'll make them pretty evenly spaced best as I can, and at the end it would probably do something like that at the ends. But it would be fairly uniform of an electric field. Why does the electric field go from left to right? Because if I were to take a test charge here and take this test charge and put it anywhere in between, it will want to go to the right. It will have a force going to the right because this positively charged test charge, and all test charges are always positive, it is going to be repelled away from the plate on the left, and it's going to be attracted to the plate on the right. So the electric field goes from left to right. So something I'd like to express is that if I were to take a couple of charges here, and I put a charge on the left side and I put a charge on the right side, what you should recognize is that in this position here, there's going to be a high potential energy, and it's also going to have high potential. It's going to have a high electric potential, and it's usually just shortened by saying potential. So whenever you see something that says a question asking about what is the potential, it's asking about the electric potential, and quite frankly it's basically going to be voltage, but I'll get into that in a moment. And so there is an electric potential on the left here, and there's an electric potential here on the right. At this location on the right, this is low potential energy, and it's also a low electric potential. So what you're wondering is, what is electric potential? And as I said, electric potential is essentially kind of voltage. So the voltage at any point, so let's just say the voltage at point A, so let's say that this is point A over here. The voltage at point A would be equal to the potential energy at point A divided by the charge that is at that point. And so if I take this charge, and let's just say that these are effectively the same charge, when I place it here to the left at point A, the voltage at that point will be equal to the potential energy at that point divided by the charge. And of course the test charge is infinitely small, or as small as I can make it, in order to just test the electric field or the electric potential at that location. And then of course the same thing would be for point B, right? So the voltage at point B would be the potential energy at point B divided by the charge. And essentially what it comes down to is that the voltage at any point is equal to the difference in potential energy. In that potential energy per charge. So to kind of clarify that, the voltage is equal to the difference in electric potential. So we have an electric potential on the left, we have an electric potential on the right, and voltage technically is equal to the change in electric potential. So right here I have expressed that voltage is the difference in electric potentials between points A and B, and so is a subscript BA because of those 2 points. If I wanted to, I could take out these positive charges and I could express this in terms of negative charges. So I'll just take in a couple of negative charges here at point A and point B, And of course, everything would be the opposite in this case, where towards the right side at position B, and I'll write that in finally, then in that case it would have a high potential there, and it would have a low potential on the other side because it wants to get away from the negative plate and towards the positive plate. All right, but typically speaking, we're talking about positive charges unless otherwise stated. That's pretty much the way it always will be, is we're going to talk about positive charges, test charges, unless otherwise stated. Also, I'd like to express the entire idea of this potential energy. So let's say that I have a couple of charges. Let me grab a positive charge here, and I put it at point A, and I'm going to just say that that has a charge, a value of Q. I'm going to take another charge and put it here, and let's just say that it has a value of 2Q, 2 times Q. All right, so in this case, they would have the same electric potential, but the charge of 2Q would have twice as much potential energy. So here's an example where we'd have the same electric potential, right, the same voltage, the same potential to drop per charge, but one has more charge, therefore it has more potential energy. So a good analogy of this is to look at, let's say, a cliff of some kind with 2 rocks. So here's one rock with a mass of m, and then here is a larger rock with a mass of 2m. And that would be quite similar, where Q and M would be analogous in this case. And then, of course, we have some height, and that height would be very similar to your voltage. So each one has the same potential energy per mass in this case, or in the case of our electric potential example with the charges, they would have the same potential energy per charge. So that's a really good analogy to think of voltage as height of a system. Later we'll talk about, rather than rocks, we'll talk about water flowing over a waterfall perhaps, and the height would still be the voltage. So now if I go back to the equation I had shown you earlier, where work is equal to force times distance, but in turn we had said it's equal to QED, so let's look at what that means, make my D look a little bit better. So if I have a charge of, let me get rid of my 2Q, if I have a charge of Q and I put it over here at a low energy position, I'm going to do work in order to move it to position A. I'm going to move it a distance, D, through this electric field, and again, it has a value of Q. So the work done to raise its potential energy is equal to QED in this case. So hopefully that clarifies a little bit of what this means and where it belongs. Let me also relate these two equations to each other. In fact, let me move this up just a little bit so I can do that. So if I look at this equation here, again, voltage is equal to the change in electric potential, or otherwise known as the change in potential energy per charge. So with that said, let me multiply each side by Q, and wait, what is potential energy, the change in potential energy equal to? Well, essentially the change in potential energy, or the change in energy of the system, is equal to the work done. So that means if I multiply each side by Q, the voltage times the charge, Q, is equal to the change in potential energy, which is, wait a minute, let me express that as the work done. But as we set up here, work is equal to QED, so let me instead replace it with that. So QED, which means that the Q's will cancel, and voltage across the plates will also be equal to the electric field times the distance. And in fact, I'm going to have to do one last thing. I'm actually going to say that this is equal to a negative ED. And that's because the energy to move a charge from position A to B is equal to the negative change in potential energy. All right, let me talk about one last thing with these plates, and that is equal potential lines. So hopefully I spell it right, so equal potential. And it basically means that it has the same electric potential. And so equal potential lines are going to run perpendicular to the electric field lines, meaning that if you were to go anywhere on this line, all of those places are going to have the same equal potential or the same electric field strength, essentially. So if I were to have a single charge, and let me just kind of clean things up here a little bit, I'll make a single charge, and of course it's going to have an electric field that extends out away from it, because if I were to put a test charge here, that test charge would want to extend out and shoot away. So that means that the electric field would actually look something like this for that charge. Or if I had a dipole would look something like this, where the electric field would extend from the positive to the negative, something along these lines, and the equipotential lines would run perpendicular to those. So it would look, let's see, right down the middle, it would look something like that, and we often put dotted lines. Okay, final. It looks something along these lines, and it actually would make sort of a circular path around the charge on this side, and something along those lines. No pun intended. And so if you've ever seen a topographical map, equipotential lines are just like the lines on a topographic map, where each part of a line on a topo map would represent the same altitude on a mountainside or something like that. All right, moving on. All right, electric potential due to a point charge. So of any point Q, or test charge Q at any distance between these, I'm going to call that R rather than D. In fact, that's the way it's often done when you have any sort of point, because you're measuring from the center of mass of the object, and so rather than using D, we'll use R, because it could be at any point from the along the radius, along the circumference of that. And so our value here is going to be that the voltage, or the electric potential, at any point where we put that test charge is going to be equal to K times Q over R. Okay, so that's for any charge. Now, if we had multiple charges, then we would have a scenario. Let's say we have, let me just erase this so I can start fresh. So let's just say I have Q1, Q2, and then I'm going to put a test charge out here. So essentially all I'm going to do at this point to find the electric potential at this location of the test charge, a little q, I'm essentially going to run this equation twice. Once where I have a value here, I'm going to call this R, I can give it any series of names if I really want to. I'll just say I call this point A. So I'm going to say that this is RA1, and this is my value of R A2. And so I'm essentially going to run this this twice. Let's just assume that Q1 and Q2 and even my test charge are all the same value. And then so I just kind of run through my equation twice. And of course my total charge there would be the addition, the vector addition of those equal potentials. Okay, so it's, if they're all positive charges, then this one's going to want to go this way, and due to Q1, it's going to want to go this way, and the vector addition of the two is going to show me which way it actually wants to go. And of course, it'll give me my electric potential. All right, so here's a little bit of stuff that's not really on the AP1 test, but I'll cover in sort of some basic terms here nonetheless. So here we have a capacitor. A capacitor is something that is essentially a couple of plates, and it's typically separated by some sort of insulator between the two. In this exact example, we actually do not have an insulator between the two. It's just air, or in fact, it could even be a vacuum between the two plates. And so the capacitance of the capacitance is measured in farads. The capacitance would be equal to epsilon naught. That is that permittivity of free space that is has that relation to K that we had talked about before in the last unit. And of course, it has a value of 8.85 times 10 to the negative 12th. We can just kind of plug that sucker in. A would be the area of the plates, and D would be the separation in meters between the two plates. What I'd like to talk about is how a capacitor works. So this is our symbol for a battery. The positive side on the left is the positive current flow, and the negative side is where the electrons are actually flowing from. So let's actually look at the electron flow for a moment. I try not to, but let's actually look at it since that's what's actually happening. So electrons want to flow to our right along this wire, up along the wire, and then to the left here, and it goes into this plate. So here we have electrons building up in this plate. And if we are able to make our value of D as small as possible, let's even see if we could, oh, no, it's not going to let me too easily the way that I drew this. But regardless, if I'm able to make the two plates as close together as possible, then what's going to happen is remember that both plates have some protons on them, and so I'll put some protons here as well. And the plate on the left, any electrons that are there, due to induction, those electrons are going to get pushed off and go down the wire, and they're going to separate the, oops, did not mean to make that happen. There we go. Oh, there I have it. And so due to induction, because the electrons don't want to be near other electrons, the electrons are going to get pushed down the wire, and they're going to want to kind of move along the wire as much as possible. Of course, they can only move along so far due to that induction. The closer the plates are together, the more the electrons want to get away from the other plate. You, of course, don't want arcing to occur between the two, and that is effectively how a capacitor works. There is a little bit more to it than that, but that is the essential idea. Here we have this equation Q equals CV, where C is the capacitance of the capacitor. C naught would be meaning that you're assuming that it's just air between the plates at that point. V would be the electric potential or voltage between the plates. Now, something that's kind of neat, just from a technology standpoint, is, of course, we're not going to necessarily just put air between the two plates, but instead some sort of insulator. And what it's known as is a dielectric. Now, a dielectric is technically a little bit more than just an insulator. What happens with any insulator, if you remember, insulator is going to have, let's say, it has its protons, and let me just kind of express it like this. I'm just going to make sort of a matrix of some protons, and I meant to change the color of that one. Give me a moment on that. Whoopsie. Go back. Here we go. All right, and so I've also got my electrons that are associated with those protons. There we go, that's a little bit better. And so what's going to happen, if I had this material, and if I had some sort of dielectric, and that's just kind of sloppy looking, so let me back that up. So imagine that this material is in between the two plates. So this insulator type material between the two plates, on the right of this material, so I'll just put a plate here and a plate here. So to the right, there is lots of electrons building up. So what's going to happen, the protons stay in place because those are part of the nucleus of the atoms of this dielectric. But the electrons will shift over a little bit, just like that. It's an insulator, so it doesn't really release its electrons, but it will shift them. And so a good dielectric will create this shift, and it's going to actually increase the strength of the capacitor if it's a good dielectric. That strength of that dielectric can be expressed fairly straightforward. So if I were to change this, so the capacitance would be equal to a big K times epsilon naught A over D. And what does that big K mean? That is the dielectric strength. It basically just means that putting that material in between the two plates is strengthening the capacitance of that capacitor, and that, frankly, is where a lot of research is going right now in capacitors. You should look to capacitors being a big thing in the future, because as they are able to increase the dielectric strength, get those plates closer and closer together, if you can get them only one atom apart, with a really good, strong dielectric constant, then you can have supercapacitors. Why is that good? Because the capacitors will be able to charge and discharge very, very quickly. They will be able to charge and discharge many, many times without any sort of degradation of the material. And so you could actually wind up having this hybrid matrix of supercapacitors and batteries in a car and charge the entire car worth of supercapacitors in just a few minutes. So that, I frankly think, might be the future of electric cars, would be some sort of integration of batteries and capacitor circuits where you have some sort of integration of having both materials. All right, that's it for the electric potential lesson. Sorry it was a little bit longer than I meant to, and the last few minutes here were a little bit bonus more than anything. With that, have a good one, and I'll see you.